What if the most dangerous weapon ever built makes no sound, leaves no crater, and kills no one yet? One detonation above the atmosphere and an entire city goes dark. No explosion, no warning, just silence. It is called an electromagnetic pulse bomb. In 1962, the United States accidentally proved it works. A city falls dark in an instant. Traffic lights freeze, elevators stop mid-floor, phones go silent, and the quiet hum of daily life vanishes. The cause is not a storm or sabotage, it is a pulse, invisible and almost instantaneous. This is the anatomy of an electromagnetic pulse, called EMP. Unlike a single wave, an EMP is a complex, three-part event. Scientists break it down into E1, E2, and E3, each with its own timing and destructive signature. E1 strikes first, a high-frequency spike rising within a few nanoseconds. This burst, born from gamma rays slamming into the upper atmosphere, unleashes electric fields that can reach over 50,000 volts per meter. It races through wires and circuit boards, frying microchips and delicate electronics before anyone can react. Even shielded military hardware feels the stress, but it is the civilian world, unshielded and interconnected, that is most at risk. E2 follows, lasting a few microseconds. Its effects echo those of a lightning strike, but it rides in the wake of E1, hitting surge protectors already overwhelmed or destroyed. Devices meant to guard against power spikes find themselves useless, leaving backup systems exposed. Then comes E3, the slow burn. Lasting seconds to minutes, this low-frequency wave acts like a man-made geomagnetic storm. It seeps into the long veins of the power grid, saturating transformer cores, pushing currents hundreds of times above normal. Unlike the quick flash of E1, E3 is relentless. It can overheat and destroy the massive transformers that keep cities alive, a threat that lingers long after the lights go out. The full EMP waveform is a coordinated assault on everything that runs on electricity. Each phase targets a different weakness, from the smallest microchip to the largest transformer. And while military systems are built with layers of protection, the civilian grid, hospitals, banks, and water plants remain exposed, their vulnerabilities mapped by the very physics of the pulse itself. On July 9th, 1962, a hydrogen bomb exploded 400 kilometers above the Pacific, far from any city or battlefield. The test, called Starfish Prime, was meant to probe the boundaries of nuclear effects in space. Its true reach, however, stunned even the scientists who designed it. Nearly 1,000 miles from the detonation, the Hawaiian Islands were thrust into an unnatural night. Streetlights across Honolulu flickered out, burglar alarms shrieked in the darkness, and a microwave relay critical for inter-island calls simply failed. For 30 minutes, the grid was blind and silent, a blackout caused not by weather or sabotage, but by a wave of energy racing invisibly through the sky. The pulse did not stop at sea level. Above Earth, the bomb's energy injected a flood of high-energy electrons into the magnetosphere. These particles formed an artificial radiation belt that lingered for months, circling the globe and bombarding satellites. Telstar 1, the world's first commercial communications satellite, launched the day after the test. It lost key systems after a single pass through this new hazard zone. Out of roughly 30 US satellites in orbit, 4 were rendered inoperable and 7 more suffered lasting damage, a loss rate no one had anticipated. Even Soviet satellites, though fewer in number, faced unexplained failures. Starfish Prime proved that a single high-altitude detonation could reach across continents, disabling both ground infrastructure and the new technology in orbit. The blackout in Hawaii and the silent deaths of satellites were not side effects. They were the first real evidence that the electromagnetic pulse was not theory, but a weapon with the power to darken modern life. The backbone of modern civilization rests on a fleet of roughly 6,000 high-voltage power transformers. These machines, each weighing hundreds of tons, step electricity up for transmission and back down for use in homes, hospitals, and factories. Unlike the gadgets that fill daily life, these transformers are not interchangeable or mass-produced. Each one is custom-built, with manufacturing and delivery stretching over 18 to 24 months, sometimes longer if foreign supply chains are disrupted. Most replacements come from factories in China or South Korea, making recovery after a widespread failure a matter of international logistics, not just engineering. When an E3 pulse sweeps across a continent, it induces geomagnetically driven currents into the grid's long transmission lines. These slow, relentless currents push transformer cores into magnetic saturation. At around 30 amperes, the insulation begins to break down. Heat builds inside the windings, oil degrades, and the core hums with mechanical stress. Protective relays may misfire or fail entirely. In severe cases, the transformer is ruined within minutes and cannot be repaired on site. The 1989 Quebec blackout, triggered by a geomagnetic storm, showed how quickly a grid can collapse when geomagnetically driven currents reach dangerous levels. In that event, 6 million people lost power in less than 2 minutes. The stakes are not just measured in megawatts or dollars. A single transformer failure can cascade, knocking out water treatment, fuel distribution, emergency communications, and hospital life support. With only a handful of spares on hand and lead times stretching into years, the loss of even a fraction of this hardware would leave entire regions in the dark for months. The vulnerability is not theoretical. It is built into the physics of the grid itself, and adversaries know exactly where these weak points lie. Foreign intelligence services have tracked open discussions of electromagnetic pulse weapons across multiple capitals. In China, research on high-altitude nuclear EMP stretches back to at least the late 1990s. Technical papers from Wuhan University and defense journals describe EMP as a weapon effect, not just a theoretical hazard. Pentagon reports from 2005 cite Chinese military doctrine that openly contemplates using a high-altitude burst to disable civilian and military electronics, targeting the very systems that keep a modern society running. Over the past decade, Chinese analysts have referenced the EMP potential of their DF-15 and DF-11 missile platforms, and recent RAND studies confirm that EMP remains a live topic in Chinese strategic thought. Russian planners have modernized their nuclear arsenal with systems like the Iskander-M, which analysts believe could be used for high-altitude EMP strikes. In 2023, Russia revised its nuclear doctrine, lowering the threshold for limited nuclear use. Western experts flagged this change, noting it allows for the possibility of EMP detonations at altitude as a form of strategic disruption, without the immediate devastation of a ground-level blast. The international community took notice in April 2024, when Russia vetoed a United States and Japan-sponsored resolution at the United Nations that sought to reaffirm the ban on nuclear weapons in space. The Russian delegation argued the proposal was politically motivated and threatened strategic stability. The veto signaled to diplomats and defense officials alike that the contest over EMP weapons has moved from theory to policy, with no consensus on the rules of the game. North Korea's official statements now routinely list electromagnetic pulse alongside nuclear and chemical weapons. RAND's 2022 threat assessment notes that Pyongyang's arsenal likely includes warheads designed to maximize EMP yield, and that delivery platforms, some sea-launched, are being developed to complicate attribution. Iranian military literature has analyzed ship-based EMP launches, with tests reportedly conducted using Scud-type missiles fired from vessels. Open-source evidence points to a growing interest in EMP as a weapon that can bypass conventional deterrence, exploiting the vulnerabilities mapped by the world's own scientific community. Each of these programs studies the same weakness: the dependence of modern life on fragile, unshielded electronics. In October 2012, a missile streaked across the Utah Test and Training Range, carrying a weapon designed not to explode, but to erase. Inside was CHAMP, the counter-electronics high-power microwave advanced missile. As it flew over its target, CHAMP unleashed a concentrated microwave pulse. Computers went dark. Security cameras froze. 7 sets of electronics, each in a separate building, shut down in sequence. No windows shattered. No fires started. The only evidence was silence and dead screens. CHAMP's pulse measured over 10,000 volts per meter at distances up to 1 kilometer, enough to overwhelm most commercial electronics instantly. Unlike a nuclear EMP, it produced no E3 geomagnetic storm and left the power grid's heavy transformers untouched. But within its focused footprint, the effect was total. Routers, radios, and unshielded microchips failed without warning. By 2019, at least 20 CHAMP missiles had entered Air Force inventory, and new versions were being adapted for stealth jets and bombers. The technology had moved from classified theory to operational reality. It was proof that a bomb capable of turning a city block dark, quietly and precisely, now exists outside the realm of science fiction. A weapon that leaves no crater, no fallout, and often no debris presents a dilemma for those tasked with national defense. In the event of a continent-wide blackout, investigators would search for clues like radiation signatures, missile trajectories, and intercepted communications. But a high-altitude detonation, especially from a disguised vessel at sea, can erase its own trail. Official testimony before Congress in March 2019 warned that forensic evidence after an EMP attack might be minimal or absent. The grid could be crippled, yet the origin of the attack would remain uncertain, blurring the line between accident, sabotage, and act of war. Policymakers face a scenario where deterrence falters. If no one can prove who pulled the trigger, how should a nation respond? A report from the Electric Power Research Institute in 2019 described the grid's vulnerability as an existential national security issue, not only because of physical exposure, but because the fog of attribution clouds every decision that follows. The gap between the threat and any credible protection remains wide, and the silence after the lights go out is matched only by the uncertainty of who, if anyone, will answer for it. Tonight, most cities glow with silent confidence in their grids. Yet each unshielded transformer, each untested protocol, leaves the line between order and blackout razor thin. While military networks brace for pulses, civilian life remains exposed. In this tension, vulnerability is not fiction, it's infrastructure. The lights stay on, for now,